In this clip, we're going to be showing the existence of a basis associated to a nilpotent matrix, and we're going to call it the nilbasis, or actually a nilbasis, because it's not unique. You'll see from the construction, because of, at the very least, you can reorder elements. But anyway, this is how it goes. So we're going to take a nilpotent operator. Then there exists several vectors and corresponding exponents, non-negative integers, which are going to be exponents, such that if we look at n raised to various powers applied to v1, and then n raised to various powers applied to v2, and n raised to various powers against vn, then we're going to get a basis. So this is the general form of that example we saw at the end of the last clip. And then also, these are chosen maximally. So in other words, if you go one step further, then that will annihilate v1, and if you go one step further here, that will annihilate vn, and so on and so forth. Okay, so that's our criteria for this being the nil basis. So that satisfies these here. We're going to call it a nil basis. Okay. And let's see. So for the proof, we've got a 3-star proof by induction. On, oh, actually, let's not call it n. Let's just call it the dimension of v. All right. So for our basis case, if we take the dimension of v equal to 1, then the only nilpotent that we have is 0. So, what do we do in this case? Well, if we take any v not equal to 0, then the result holds applied to this one. So, namely, if we apply n to this vector, then we get 0, so that satisfies condition 2. And for the first one, we just have the singleton list that looks like v1 by itself. Here, I'll put it in parentheses to make it look sad and lonely. That's our basis. Okay, kind of trivial. Whatever, it's the basis case, it's usually trivial. So, okay, so, and then I guess you can notice that similarly, this holds for when our nilpotent is the 0 operator, no matter what the dimension of v is. And we just do the same thing, we just take any basis. And then all of the VKs form a basis, and all of our NVKs are going to be equal to 0. So you just have the basis of VKs, blah, blah, you're done, the end, you win. Okay, so we can rule out that case and assume then that we're dealing with the situation where our operator is not the 0 operator. Okay, so suppose now that we've got a dimension of v is greater than 1, and that the result holds for all vector spaces of smaller dimension. So strictly less than dim v. Okay. So then, let's see. Well, n is nilpotent, right? It's our beginning hypothesis. And so then we know that n is not injective. Has to have some non-trivial subspace. And since we're on a finite dimensional space, this means our operator is not invertible, so not surjective. And so then that tells us that the dimension of the range of n is strictly less than the dimension of V. So the inductive hypothesis applies to it. And notice that the range of n is an invariant subspace under n, so it's a well-defined to talk about this restriction. Okay, so thus there exists V1 up to Vn in the range of n, such that if we look at n to m1 V1, so here's all the powers of n applied to V1, including the 0th one right there. And then you also do the same thing for V2 and Vk all the way up through Vn. Like this. Then this is going to be a basis of the range of n. Okay, and then we can also see that if we take n to the m1 plus 1 and apply it to v1, then that's going to equal 0, and that's going to be true for all of them. That's because this is the second part of the inductive hypothesis that we are assuming. Okay, so now since we've got each Vj is in the range of n, this means that it's the image of something, right? So there has to exist some uj in V such that n of uj is equal to Vj. So what we're doing is we're sort of like backing it up one step in terms of the hitting by ends system. So now, so what we're going to do is claim that if we look at n to the m1 plus 1 applied to u1, n to the u1 u, and so on and so forth. So here we've got n to the mn plus 1 applied to un here. Okay, so we claim that this guy is the required basis of V. Okay, and so notice, I'm just going to go back here and grab these guys. And let's make them light green or something. Okay, so here we've got, NU1 is V1. So these guys are equal, right? And NUN is equal to NVN. And so forth. So there's all kinds of these things being equal all the way down, including up here at the end. So these are all equal to each other. Okay. But now we also have these new ones that we've picked up by looking at pre-images. Okay. In the next clip, we will continue the proof.